Yeah. Hi everyone. My voice is audible.
Yes, you are audible.
Yeah. So in today class, our main focus is on test bench architecture for our DUT and our what are the features our DUT will support and what is the verification scope of this project PCIe Gen 5 MAC layer functional verification. So what is the verification scope and what are the TB components and what are the interfaces we have. So, overview, we will discuss overview of the project and then we will take questions if anyone has any questions related to the project. So, we will take, so yeah. So, this is our test bench architecture. This is our test bench architecture. So, in our project, we are verifying PCIe MAC layer. PCIe MAC layer. So, in our project, we are verifying PCIe Gen 5 MAC layer. So Mac layer. So in Mac layer, we can have multiple features, multiple PCI features like scrambling, decoding, and we also have LTSSM. So LTSSM is for link prime. LTSSM is for link prime. So this project scope is verification of LTSSM, and we will check how order set exchange between both upstream port and downstream port, and how link progress, LTSSM state progress is happening from detect state to detect quite detect active, and then how it goes to polling state and polling substates, and then how it going to configuration state. So our project is PCI Gen 5 MAC layer functional verification. So we are not verifying the scrambling, we are not verifying the encoding, decoding. So our focus is on LTSSM state verification, whether all valid state transitions happening or not, and whether corner case transitions are happening or not under timeout conditions and under different protocol rules, whether LTSM corner state transitions happening or not. So those things we will verify. So it means we will completely verify the LTSM. We will completely verify the LTSM and we will bring link to zero. We will bring link to zero initially at Gen 1 speed. We will bring link to LTSM will be trained to the L0 state at Gen 1 initially. So after that, it will try for the higher speed. It will go to recovery state. From L0, it will go to recovery state. From L0, it will go to recovery state and it will be trained for Gen 5. Gen 5. So in this project, remaining Gen 2, Gen 3, Gen 4. So those features also we can enable. So that coding also implemented. But in our verification scope, so we will check whether link bring up happened for the Gen 1 or not. So after that we will check whether link bring up the speed change is happened from Gen 1 to Gen 5 or so this speed change feature we will check and link with is fixed. Here link with is configured. So we can configure link with to 4, link with to 8, link with to 12, 16. We can configure, but in this project we are configuring link with 4, link with 4. So these are configured. Link with is configurable. We have the pipe interface link with. We can configure from the test bench top. So I will draw the overview of the block diagram. So here what we are verifying is we have one PCIe device. So let's assume this is the root complex. This is downstream port, and we have another PCIe device. This is upstream port. This is upstream port, and assume this is the PCIe endpoint. PCIe endpoint, and between this we have the link. Between this we have the link, PCIe link. PCI link. So our task is to verify the PCIe MAC LTSSM. PCIe MAC LTSSM. So we cannot verify LTSSM independently without having the peer device. Without having peer device. So for verifying the LTSSM, we need two ports. One is upstream port and another is downstream port. So here downstream port you can assume as a root complex. Upstream port you can assume as a endpoint. So in our project we have one RTL module. We have RTL module. So RTL module, and this is the MAC PCIe MAC PCIe MAC RTL module. PCIe MAC RTL module. So it has the two interfaces. It has two interfaces. One is DLL. One is data link layer pi interface, data link layer pi interface. So another is pipe interface. So another one is pipe interface. So here we can configure this MAC as downstream port as well as upstream port. So it means this MAC, our RTL, we are configuring same RTL two times, one time as downstream port and another time as upstream port. So it means in our TV top, so this one is our TV top. So in TV top, we are instantiating this RTL module. We are instantiating this RTL module. So let's say instance one, and instance two. So we are instantiating this RTL module two times in our TV top. So first time we are configuring RTL as downstream port, and second instance we are configuring as upstream port. So it means same RTL we are reusing. Same RTL we are configuring one time as downstream port and second time as upstream port. Second time as upstream port. So our RTL has two interfaces. One is data link DL pi interface, another is pipe interface. So with the pipe interface, both upstream and downstream ports are connecting. Both upstream and downstream ports are connecting. And in our project, we don't have electrical pipe. We don't have electrical pipe. So in our project, we don't have electrical pipe. Means we don't have analog pipe. We don't have analog pipe. So for simulating the analog pipe, we have agent. We have agent called LTSSM1 agent. LTSM1 agent. LTSM1 agent will simulate the electrical pi behavior. Will simulate the electrical pi behavior. And here we have the LTSSM. So here overall we have the data link layer DLL pi interface, and this side also we have DLL pi interface. So this pi interface, for simplicity, it will be split into three small agents. Three small agents. One is TX agent. TX agent. TX agent. This is active agent. TX agent, this one is active, and another is RX agent. RX agent, this one is passive. This one is passive. By using TX agent, we will manage the protocol traffic between data link layer and physical layer. It means by using TX agent, we can generate TLPs and DLPs. TLPs and DLPs. So by using RX passive agent, we collect TLPs and DLPs. We collect TLPs and DLPs for achieving the coverage, for checking the coverage and for checking the scoreboard. So other side, for upstream port also, and so out of three, one is TX agent, active agent, another is RX agent, passive agent. TX agent for generating TLPs, DLLP protocol traffic. RX agent for collecting TLP and DLLP traffic. And we have another agent called LTSSM2. LTSSM2 agent. So this one is for guiding the LTSSM. We can force LTSSM to detect state. We can force LTSSM to detect state and to know the link status, link operational status to data link layer. So we have another agent called LTSSM state. So by using this LTSSM2 agent, so we can get physical layer operation by operational state, like whether link is operating or not, link up equals to 1 or so by using LTSM2, we will get the link status to the data link layer. So here this side also, so broader, this is the pipe interface. Broader view, this is the pipe interface, but again this will be split into three. This will be split into three. So one is TX slave, and another is RX slave, and another one is LTSSM1. So LTSM1. TX slave will TX slave will track outgoing order sets. TX slave will track outgoing order sets and it will predict. So it will track outgoing order sets. It will track order sets and it will predicts the next LTSSM state. Predicts next LTSSM state. So RX state is this one is the passive. It will simply collect coverage for order sets. It simply collect coverage for order sets. Simply collect coverage for order sets. And we have this LTSSM1. So pipe interface we have LTSSM1. So this one simulate the pi electrical block. This one simulate pi electrical layer. This one simulate pi electrical layer because here we don't have physical wires. We don't have physical wires. So here we will use DLM ports only. See this. This is so in real time we have the physical wires. Real time we have physical wires. But here we created a link by using the DLM ports only. DLM ports, and in between we have one component called adapter. Some component called adapter. So adapter will work in two modes. Mode 1 and mode 2. So mode 1 is bypass mode. Bypass means it won't inject any errors. Simply it will forward incoming order sets, incoming TLPs, DLPs. So in bypass mode, adapter will forward incoming TLPs, DLPs, order sets in error injection mode. Second mode is error injection mode. So in error injection mode, it will inject errors. It will inject errors into order sets. It will inject errors into order sets. So by injecting errors only, we can achieve the LTSM corner case coverage. LTSM corner case coverage. So ideally LTSM states will be like detect. So detect, then it will go to polling, then it will go to config, and then it will go to L0, right? Then it will go to L0. But how to achieve polling to detect, how to achieve conflict to detect. So this corner cases achieved by injecting errors using the adapter component. This corner cases achieved by injecting errors using adapter component. So for injecting errors, we will develop test cases. We will develop sequence error injection sequences. So the same environment. See here for root complex for downstream code, what we discussed, we have data link layer, DLL pi interface, DLL pi interface, other side pipe interface. DLL pi interface has three agents. DLL pi interface has three agents. So one is TX active agent, TX active agent, it will generate DLP traffic, and RX passive agent, it will collect DLP for coverage, and we have LDSM2 agent for getting for knowing the link status and for directing link into detect state. And other side we have the pipe interface, other side of downstream port, a MAC layer, we have the pipe interface. Again, pipe interface has three agents. One is TX slave agent, another is RX slave agent. TX slave agent will track outgoing order sets, and it will predict next LTSM state. So and same way we have the RX slave agent, which will monitor incoming order sets for collecting the coverage, for sampling the coverage. So it will monitor incoming assets, and we have the scoreboards. We have total four scoreboards. We have total four scoreboards. We have total four scoreboards. So scoreboard will compare transmitting TLP DLPs and received TLP DLPs. Scoreboard will compare transmitted and received TLP DLP traffic. And here also we have TX slave, RX slave. So here also it will compare. So we have another scoreboard for downstream scoreboard too. It will compare transmitted and received order sets. Transmitted and received order sets. So same environment will be reused. Same environment will be reused for the upstream port. It means for upstream port also we have DL pipe interface and we have the pipe interface. And for upstream DL pipe interface we have again three agents, and upstream pipe interface we have three agents, and upstream DL pipe interface also we have again three interfaces. So here we will get more clarity. See here, this one our upstream port and this is a downstream port, and it has two interfaces. MAC layer has two interfaces, downstream MAC layer has two interfaces. So here this is DL pi interface, and this one is pipe interface. Sorry, this one. So this one is PL pi interface, and this one is pipe interface. And again this is pipe interface, and this is DL pi interface. So by using DL pi interface has three agents. One is TX master upstream agent, another is RX passive upstream agent, and LDSM2 upstream agent. So TX master upstream agent will generate TLPs and DLLPs, and RX passive agent, upstream RX passive agent will collect DLPs, and this transmitted DLPs and received DLPs will be compared using the upstream scoreboard. Scoreboard, and we have coverage, and we will also collect coverage by using these two interfaces. And pipe side, as we discussed, we have TX slave upstream agent RX slave upstream agent. TX slave upstream agent will monitor, it will track outgoing order sets, it will track outgoing order set and it will predict the current LDSM state. Based on the outgoing order sets, it will predict LDSM state and it will inform the predictor. So based on the current LDSM state, we can inject the error to achieve the LDSM corner cases. And this one RX slave agent, it will monitor order sets for sampling the coverage. So by using TX slave interface, RX slave interface, so coverage will be sampled in 5 coverage upstream component and this TX transmitted order sets, received order sets will be compared using the pipe scoreboard upstream. So for upstream, we have two coverage components, two scoreboard components, and total we have 6 agents. Same environment will be replicated for downstream also. So downstream also we have similar interfaces, DL pi interface and pipe interface. And again we have 6 agents and two scoreboards, two coverage components. So here adapter is the game changer. Adapter is the game changer because without adapter we cannot achieve LDSM corner case coverage. Without adapter component we cannot achieve LDSM corner case coverage. So by using adapter component we will inject the errors. We will inject the errors. So adapter has that error injection logic. So in sequences just we need to enable the error injection logic. So based on we need to select a particular state for injecting the errors. So based on the selected LDSM state, adapter will inject the error. So we will achieve uh, corner case, LDSM corner case state transition. So anyone has any doubts regarding the TV architecture?
Shiva, can
Yeah.
you, in this architecture, right? Can you please explain the data path again from where we are going to do the transaction and what all things we'll be checking it? The data transaction path, can you please explain again?
Yeah. See here we will create. So what are the type of sequences we create? Just we will explore. So by using LTSSM1 and LTSSM2, so we will reset this. We will reset this MAC layer by using LTSSM1 and LTSSM2. So we have the reset sequences. So we have the reset sequence for upstream, and the reset sequence for downstream. So by using these two sequences, we will create one virtual sequence. We will create a virtual sequence and we will run these two sequences simultaneously on these two LDSM one upstream, LDSM one downstream sequencers. So after that we have link up sequence one, link up sequence two. So again both we will execute by using the virtual sequence. So after doing reset and the link up, the LTS system will start. The LTS system automatically starts state transitions. It will automatically progress. After reset, it will automatically progress from detect state to polling to config, and automatically it will go to L0. Will go to L0 and initially it will try for the Gen 1. Initially it will try for the Gen 1. So then we need to check the waveform. Then we need to check. So after bringing link to the Gen 1, after bringing link to the Gen, so we need to check whether all state transitions are valid or not. And from detect to polling, uh, from detect to polling valid, so that electrical ideal transition happened or not. In polling substates, valid TS1, TS2 order sets exchanged or not. And in config state, valid TS1, TS2 order sets exchanged or not. Link and lane width are properly negotiated or not. Those things we will observe on the, those things we will check on the waveform. Check on waveform. And if any issues, we need to check the RTL. So, but in this project, we will check, we will observe whether the valid order sets exchanged for each state transition or not. So first in TB top, so in TB top, TB top, in TB top, both downstream port and upstream port are configurable. So first we will configure downstream port for Gen 1, downstream port for Gen 1 and upstream port for Gen 1, and then we will start the reset. We will start the reset. So then automatically LTSM will progress and it will come to L0 Gen 1. So actually we will observe this one. So after that we will configure LTS, both LTSM1, sorry, downstream port and upstream port for Gen 5. Downstream port Gen 5, upstream port Gen 5. And again we will start reset and link up sequences, link up sequence test cases, and we will observe. Then we will observe whether initially link up happened for Gen 1 or not. Initially link up happened for Gen 1 or not. So after Gen 1, so because we configured both downstream upstream for Gen 5, so we will check after entering into Gen 1, it entered recovery or not. It entered recovery or not. From recovery, it will go to recovery receiver lock, recovery speed change. And from there, recovery speed change, it exchange electrical ideals or not. And how, whether speed change happened for Gen 5 or not, we will check. So after speed change for the Gen 5, it came to L0 or not. So that one we'll check. Finally, we will check whether LTS system is settled for L0 with Gen 5 or not. So that future we will check, and between each state transition, valid RS sets are exchanged or not. So those things we will observe. Those things we will observe. So after that, by using the adapter, we will create a error injection sequences. Error injection sequences. There we create a sequence and we will select the state. We will select the LTSM state. LTSM state. So based on the LTSM state, adapter will inject the error. So adapter will have some capability like adapter can inject error in particular symbol of TS1 order set. So TS1 has 16 symbols, right? So adapter will randomly choose particular symbol out of the 16 symbols and it will inject error like changing the link with changing uh, rate ID. So like that, adapter randomly inject error in TS1 order sets. So then we will observe whether LTSM, so after injecting the errors, receiver side, where we will observe whether LTSM enter into detect state or not. Next valid state. The LTSM corner state transition. So those things we will check. So likewise, by using error injection sequences, we will inject errors on all LDSM states and we will check all corner cases. So for this all state transitions, for this all state LDSM state transitions, so we will implement a coverage. We will implement a coverage and we will check. So our task is to achieve coverage for all LTS and valid state transitions, corner case transitions. So first we will achieve LTSM coverage. LTSM coverage. So after that we will focus on protocol traffic. After that we will focus on protocol traffic. So we will create a sequence for TX master agent So for TX master agent, we will create sequences for generating TLPs, for generating DLLPs, for generating TLPs plus DLLPs mixed. So we will generate three type of sequences. This is a different length. See here, so here the protocol, these transactions are not packet level. It means we not follow the packet format because see here we simulating the behavior. Just we are simulating TLDL behavior. So we will randomly generate some payload length for TLPs, DLPs. So TLP type sequences, separate DLP, DLLP type sequences, and separate mixed sequences, TLP, DLP sequences. And by transmitter agent will transmit these TLPs, DLPs, TLPs, DLLPs. So same sequences we will reuse for this TX master downstream agent also. So the same sequences we will send through this TX master and same sequences we will send through this TX master. It means both devices are sending same data. Both devices are sending same data. So here we will expect the whatever we are transmitting same data we will expect here. RX passive upstream agent, RX passive agent. So we will compare this transmitted and received data because we are using the same sequences for this TX master downstream agent and TX master upstream agent. By using the virtual sequence, we will start both TX master upstream agent and TX master downstream agent. So this TLPs, DLLPs go like this, and through adapter they will come to here. So this TLPs, DLLPs go like this, and they will come here. So because the data is same, we will compare this TX master upstream agent and RX passive upstream agent. So by using this upstream scoreboard and downstream scoreboards. The same way order sets, the order sets both will exchange the same order set. So transmitter slave upstream agent will track transmitted order sets and receiver slave downstream will collect those for coverage. And here also TX slave downstream will send the same order sets and RX slave upstream agent will collect the order sets. So here we compare this TX slave upstream order sets and RX slave transmitted order sets and received order sets inside the upstream scoreboard, pipe upstream scoreboard. And coverage we will collect pipe coverage upstream component. So clear, right? Hello.
Yeah, Shiva.
Yeah, here see by for looking it is complex. For looking it is complex, but actually we implement sequences for single component and we will reuse. We will reuse by using virtual sequences. But here the complexity is like we have four scoreboards and four coverage components. So for one component we will do in live classes. So for other component just same logic you try to mimic the same logic. So if we go So this is the coverage we will achieve. So final coverage we are getting around 95% for downstream port. See here we cover all LTSM corner cases. See detect quite to detect active. This is normal transition. Active to polling. This one is also normal. And the polling active to config. This is also normal. Polling active to detect. So this one is corner case. So this is achieved by using the error injection. So this is normal, this one also normal, this one also normal. So again this is corner case. So this one achieved by using error injection. So first without error injection we will check the waveform and we will check the coverage. So then we will get only less coverage. We will get less coverage. So after injecting all the errors for achieving these corner cases, so we will get more coverage. So this all detect transitions are corner cases. So these bins will be covered by injecting errors only. These bins will be covered by injecting errors only because normal condition these state transitions won't happen. So we need to inject error, we need to make timeout, or we need to. So this one is for downstream device coverage only downstream. Yeah, next we will collect coverage for order sets, different type of order sets. So training sequence 1 for Gen 1, training sequence 2 for Gen 1, TS1 for Gen 5, TS2 for Gen 5, electrical ideal order set, electrical ideal exit order sets, keep to start of data stream ideal. So likewise for both downstream and upstream for both TX and RX slave agents. And we will also generate different TLPs with minimum size, maximum size. For that also we should count it. So today I will send RTL code. So I will share RTL code. Just analyze the RTL code. So I will share RTL code. Just analyze RTL code. So what are the blocks we have? So briefly we will I will go through all. So we have main LTSSM logic, main LTSM logic. So just go through this one I will show. See the LTSSM, this is configurable. This is configurable. So the generation is configurable. So we will configure one time for Gen 1 and second time for Gen 5 and we will check whether link is trained for Gen 5 and whether it is settled at L0 Gen 5. So the LTSM is configurable. So we can configure the generation up to Gen 5 and device type. See, this is the main parameter. This is main parameter. So 0 means it act like a downstream port and 1 means it will act like a upstream port. And we can also configure the pipe. We can also configure pipe width for different generations. Gen 1, Gen 2, Gen 3, Gen 4, Gen 5. So we can configure and we can also configure lane numbers. We can also configure link width. We can configure lane numbers. So this is code, just go through this one. So next we have the order set generator. So how order sets are generated based on the generation, based on whether Gen 1, Gen 2. So because order sets are different for each generation. Order sets are different for each generation. Here, so we have input bit 2 down to 0, 2 down to 0 gen. So we are getting input generation. See 0, 0, 1, 0, 0, 1 means gen 1, 0, 1, 0 means gen 2. So if it is gen 1, gen 2, these are transmit preset parameters are selected. See if it is Gen 1 and Gen 2. Gen 1 and Gen 2, so it is selecting the particular order set type, particular order set type and lane number. So lane number we configure inside TV top and generation also and the symbol. So these are different flags and skip order setting. Gen 1, Gen 2 skip order set means this one and electrical ideal order set this one. TS1 order set first symbol. So this one TS1 identifier BC. First symbol TS1 identifier is hexadecimal BC and link numbers. So link number if it is 0, 0 it will add pad values. So second symbol is second symbol is link number. Second symbol is link number. So in polling state, polling state initially polling state still link number is not negotiated. So link number is 0. Polling state still link number is 0. So that time it will select second number with pad values. F7 means pad value. Pad value is F7. So if link number is negotiated, link will be assigned. Link number will be assigned to symbol 2. So based on the rate. So if rate equals to Gen 1, so this bit. So Gen 1 bit is asserted. Gen 1 bit is asserted and this value is assigned to rate ID. So this symbol is rate ID. So if rate is Gen 2 means these two are asserted. Gen 3 means these 3 bits are asserted. Gen 4 means these 4 bits are asserted. So we saw right in theory class TS1 order set format. We studied all the 16 symbols. So one of the symbol is rate ID. So based on the generation, configured generation, this TS1 is configured. This TS1 rate ID will be selected. So same way speed change, the loop back. So these, see in our project, these are, we are configuring this. These values are we are configuring, but in real project there will be registers. So by reading the configuration registers. So here in this project we don't have configuration space configuration registers, but in real project, real complete endpoint or complete PCIe device, there will be configuration space. There we have registers, right? Based on the target speed, the speed will be selected. So basically, we have loop back bit. So in control registers, device control registers, we have loop back bit. So if software asset loopback equals to 1, then this symbol will be assigned this value. So otherwise this is 0. So here we manually controlling these bits. We are manually configuring, but in real time there will be configuration space and control registers. So based on the control register information, TS1 order sets automatically generated based on the generation. So finally we have last symbol. So last three or four symbols are related to TS1 identifier. This value is TS1 identifier. So in the same way for TS2 also, so initial first symbol is BC. This one TS1 identifier and link number is selecting and rate ID. So same whatever symbols we have for TS1, same symbols for TS2 also. So based on the generation, it will select different values. So finally, TS2 identifier is 45. TS2 identifier is 45. So, so these above are Gen 1 and Gen 2. So now for Gen 3, Gen 4, Gen 5. And the pipe width, based on the pipe width configuration and generation, so we have different logic. So here in this RTL, we commented for different pipe widths. So we stabilized the code for only pipe width 16. So this code is commented. So after this code, if you want, you can analyze this code. So this RTL supports encoding, scrambling also. So you can enable it. You can uncomment this RTL code, and you can try to validate that encoding, decoding, and scrambling. So based on the link width and generation, based on the pipe width and the generation, so we have the same logic, but based on the pipe width and generation, we are enable this one. So above is for pipe width equal to 8, because here this project supports Gen 5, so we enabled pipe width 32. Pipe width 32. So based on the order sets, it will do different tasks. We'll generate order sets, data symbols. So just go through this code. So in real time, like RTL is black box only. For us, RTL is black box only. But for understanding, you can go through this one. So this order set block is for generating order sets based on the generation. And next we have TX LTSSM and TX LTSM, RX LTSM. So we have other blocks also. We have other modules also related to scrambling, descrambling, and LFSR. Scrambling, descrambling, LFSR for generation 3, 4, 5. So mainly just go through LTS system block. So order set module and main LTS system and TX LTS system and RX LTS. And also go through this timer block. So in LTSM for every LTSM state, so there is timer, right? So the timing value is the timer is started after the timer will be started after entering particular LTSM state, and it will count in background. It will run in background. So based on the if the timer reach limit, if the timer reach limit, so it will exit to valid state. It will exit to valid state. So let's say in configuration state, if timeout happens means, so it will go to detect state. So that time is calculated inside this timer module. So based on the pipe width and generation, mainly based on the generation and the required time, it will start timer. It will start timer in the back. It will start timer in the background. So first it will start. See here we have this equation conditional so. So initially after LTSM entering into particular state, so it will raise this flag, start flag. It will raise this flag. So it will raise this flag. So after that the timer will be enabled. Timer will be enabled. Timer will be enabled and timer will increase. Timer will count in background and that count flag is tick. Whenever timer reached maximum boundary, then it will accept this one tick symbol. So tick greater than timer enter. See here. So let's say we are in configuration state or polling state. Configuration state timeout condition is 12 milliseconds. 12 milliseconds. So after completing 12 milliseconds, so the tick will be greater than or equal to timer interval. Timer interval is 12 milliseconds and the tick will run background. Tick will run background. If tick is greater than or equal to timer, so timeout will happen. The timeout equal to 1. Timeout is the output signal. So timeout is the output signal. So based on the timeout, if this timeout is 1, LTSM will transition to valid state. LTSM transition to valid state. So just analyze this timer also. Timer. Next to check TV top our PCIe top. So this one is our top module. So this one is our top module. This we will instantiate inside our TV top. So this one we will instantiate in our TV top. Tomorrow we will do this. So just analyze this one also. So TV top has LDS so different modules. So in TV top, all MAC layer subblocks are instantiated and they are connected. So they all are instantiated and they are connected to both DL pi interface and pipe interface. Means like DL pi signals and pipe signals. So we will instantiate this top module inside TV and we will do necessary connections for it. So anyone has any doubts regarding? So anyone has any doubts regarding the project? So Rohit Reddy, Pavitra Rahul, Shrey, Shahraj, Vikas, Shrikant,
No, Shiva.
Kumar, Shivakoteshwar.
As
So
of
this is about our project. So yeah, Rohit, Rohit.
as of now, that's fine. I understood, but I would like to take a deeper look into that because I don't have any previous knowledge on like theory knowledge. Also, I don't have PCIe, but I understood a little bit. Maybe after in the coming days, I will definitely I'll ask you a few questions on this.
Yeah, okay, yeah. Yeah, Selva.
Yeah. Hi Shiva, this is Srikanth.
Yeah, Shrikant.
Yeah, we don't verify that electrical related physical layer. No? Only uh, you told some
See,
physical layer.
in industry also, we not verify the electrical physical layer. So that
Okay.
is verified by AMS engineers, analog mixed signals.
Okay. So that means in this interface, can we deal with both STP and SDP also?
Yeah, yes, we are generating pseudo DLPs and TL. Yes, you are saying STP,
And SDP. Uh,
STP and
that means,
SDP.
yeah,
The,
generally without interfering transaction layer, STP will generate na SDP. And
yeah,
with,
but
yeah,
yeah, that one, see, as I told previously, so here we not simulating packet level. So
okay,
TLPs, we are not simulating at packet level. So we are
okay,
generating some random data and we are encapsulating the data by using start and end. So based on the data, we generate random start and end for encapsulating TLP and DLP. So we will first of all we will randomize payload size. So based
okay,
on the payload randomized payload data, automatically we will create a logic. That logic will generate payload specific start and end. So the same thing we will decode at receiver side and we will validate whether data is correctly coming or not.
okay. And we can also verify here X by 4 and X by 16 lanes like this, or only one lane configuration.
Yeah, here the code is stabilized for only one lane, but but the RTL supports configuration. You can configure, but see in some RTL lanes code is commented, right? So
Uh,
because some error issues and all. So if you want, you can that enable the uncomment that RTL logic, and then you can configure that lanes, different lanes linkage.
okay. Yeah. And which tool we are using actually? This one, we are doing
Yeah, yeah, we will use Vesta sim.
first one. Yeah. Okay. Okay. Thanks, Shiva.
Yeah, okay, thank you. So any other doubts anyone have?
Hello.
Yeah,
Actually, pipe we using pipe to like loopback type we are verifying, right? TX to RX and RX to TX.
yeah, yes, yes, yes.
Okay,
So because
which version
yeah,
of pipe we will use?
which
Version pipe version.
see it's like we are not mimicking the real pipe.
Okay.
Yeah,
Similar kind of things.
yes. So just our task is just to get some understanding how the pipe is there, how the DL PI interface is there, how order sets and protocol traffic is happening. So this is a learning project, right?
Yes.
So actually for Gen 5 we need to use pipe interface above pipe 5.2, 5.1, 5.2. But here we will not use all pipe signals also. So we will use the required signals like pi status.
Yes.
Yeah. So any doubts? Amit Kumar, Shiv Kodeswar, Vikas Kumar, Rahul. So if no doubts, we can end the class here.
Yeah. Okay, sure. Thank you.
Yeah, okay, okay. Thank you. Yeah, okay, then we will end the class.
Hello.
Yeah, hello.
We did you share the RTL code today?
Sorry, yeah, I will share in the WhatsApp group.
Okay. Thank you.
Can we, hi Shiva?
Yeah, I am.
Yeah, when we are planning to go further, like TV, I mean coding point of view.
We need to install tool, right? First of all, so tomorrow we'll install tool, and if time permits, we will try to develop TB top and interface, and we'll integrate RTL to TB top.
Okay, so this Questa sim will support normally, normal Questa sim will support for this PCI.
Yeah, yes, yes.
Okay. Okay, thanks.
Okay, thank you.
Shiva, last one. Uh, which specification are you we are referring to right now for PCI 5?
So we not referring any specification. So the project agenda is to get some. It is educational purpose only. So the project purpose is to get hands-on experience on PyMac verification and to understand how RSet flow is happening, how LTSSM state transitions are initiated, how link bring up happening for different generations Gen 1 and Gen 5, and how the actual protocol traffic is the TLP's DLP's transmission is happening. Mm.
Uh,
Okay, why I'm asking was because I would like to understand like a different layers are there at physical layer, transaction data link layer. So I would like to have a reference. Like if you have anything, can you share that thing also?
Yeah, regarding this, for understanding this one, so you need to have you need to have the knowledge. What are the order sets and what are the so you need to have what are the order sets and you need to have knowledge of LTSSM. LTSM and different LTSM states and function of each LTSM states and what are the order sets exchange negotiated in each of LTSM states. So that much is enough. So you no need to have complete knowledge of TLP structure, transaction layer, data link layer. So that
Okay.
one, like theory classes you attended, right?
Theory I didn't, but I enrolled in that.
So theory classes, so in group I will tell some of the classes. Like you need to focus on some class. So yeah, so here from day 22. So this one also we are not covering. So this is not for 22, not for 22. We use the equalization. So from day 24, day 25, 26, 27, 28, 28. So completely you need to focus on LTSSM. So complete
Okay.
LTSM states. So then, so from 21, from day 21 to 28.1.
Okay, Shiva.
Hi Shiva, one question.
Yeah.
Currently in industry point of view, like PCI Gen 6, they are asking. Like I want to
Mm.
understand, like it's much difference are in PCI Gen 5 and Gen 6, or how it will be. Or if you are going to learn that PCI Gen 5 is enough to understand that PCI Gen
Yeah,
6.
if you understand Gen 5 completely, so for learning Gen 6, so If you want to learn by yourself, it will take 2 weeks. Within 2 weeks, you can learn. So in Gen 6, what major changes happened is in transaction layer. So instead of having the dynamic header, like instead of adding the TLP prefixes, so they introduced one field called OHC, orthogonal header content. So what they made is in Gen 6 header, they made modular. So header is more modular. So instead of adding prefixes, they made header modular. So it means the OHC, orthogonal header content, it is another header, like another submodule. So based on the type of TLP, so based on the configuration, OHC will be changed. So that is the main change in transaction layer. Coming to the data link layer, so in data link layer, they removed LCRC and sequence numbers. So they removed TLP encapsulation data link layer. They removed CRC for DLLP. CRC for DLLP because so the reliability is happening at fleet level. Gen 6 reliability happening at fleet level. So previously reliability happened at TLP level. If any error like LCRC or sequence error happen, so that time by using the NAC DLLP, we get the sequence number. So the TLP will be replayed, right? So reliability happened at TLP level. But in Gen 6, reliability mechanism happening at fleet level. So fleet has, so instead of having CRC for TLPs, sequence number for TLPs and CRC for DLLPs, so in Gen 6 they introduced CRC for fleet. So fleet is nothing but a fixed size payload, fixed size transmission unit. So it is 256 bytes. So it can include DLPs, TLLPs. So the transmission is happening. The transmission using the main change is the transmission unit. In Gen 6, the transmission unit is flipped.
Okay, okay. I will look into it. Yeah.
And we have like, so in Gen 6, another change is there is no ACNAC DLLPs.
Okay.
There is no ACNAC DLLPs. So instead we have forward error correction, FEC. So the reason is because the Gen 6 works at very high speed, So at high speed it, it induces more link errors, more bit error rate. So more bit error rate, so it increases what is overhead. More bit errors means so more replays are possible. So it will increase overhead, control overhead. So for reducing that, so they are correcting. So for detecting, we have the flit CRC. For correcting, we have forward error correction. So by introducing forward error correction, so they are reducing with control overhead and latency. So, so the major changes are flit. The major changes flit and encoding, PALM encoding. So logical encoding 1 bit by 1 bit and electrical instead of NRZ they are using PALM encoding, PALM 4 encoding.
Yeah. Okay, Shiva. Yeah. I will. Yeah. I got some idea. Yeah. Thank you.
Thank you. Anyone has any doubt?
Upload those notes.
So which one? Which notes?
So only day 28 is uploaded, right?
Day 28. Okay,
I,
I will
I
check. I
I
will check.
mentioned you. Yeah.
Yeah, day 28 upload. Yeah, I will upload this notes.
Yeah, yeah.
So okay then. Thank you. Thank you all.